So first of all, thank you very much for the opportunity to talk to you today. So yeah, I'm going to be presenting some results from the third catalogue of Fermi gamma ray pulsars, which is a work that has been ongoing in the Fermi collaboration for many years. But I'm giving this talk mostly on behalf of David Smith, who's been leading this effort kind of thanklessly and tirelessly for many years. So I'll give some highlights from that, and also towards the end of the talk also present some new MSPs that we've been finding pointing Meerkat at Fermi sources as well. So just to start off with, I thought I'd give some background for the radio astronomers, but we're searching for gamma ray pulsars in this case. And the detector we're using is this large area telescope, which is this box on top of the Fermi satellite, which is a gamma ray detector sensitive to gamma ray photons with energies between a few tens of MeVs and a few hundred GeVs. And this image is the all-sky view that Fermi's built up over the past 15 years of data. So it continuously surveys the sky, and it's been doing so for 15 years, and detecting pulsed gamma ray emission from pulsars. This is a bit of a timeline on the pulsars that Fermi has seen. So prior to Fermi's launch, there was only 10 gamma ray pulsars known that had been detected by previous instruments. And within the first year of the Fermi mission, that number had increased to 50 when the first Fermi catalogue of gamma ray pulsars was released. And over the past 15 years, that number has been steadily increasing until, yeah, as Paolo said, we're now at nearly 300 pulsars. So in 3PC, we're cataloguing 294 pulsars, so very close. But we actually have detected new pulsars, new radio pulsars in another 30 or so gamma ray sources. So we know that we've detected gamma ray emission from more than 300 pulsars, just not gamma ray pulsations yet. But that population is split roughly halfway between millisecond pulsars and young pulsars. And those young pulsars are also kind of split 50-50 between pulsars that were found in radio and X-ray surveys, and then the gamma ray data was folded using the ephemerides. And the other half were found by directly searching for gamma ray pulsations in the LAT data itself. So yeah, compared to the last iteration of the catalogue, we have more than twice as many pulsars, and also for each pulsar, we have more than twice as many photons because we've been observing for much longer. The catalogue itself contains many more things than I can present in 12 minutes. So I wanted to just give this kind of diagram of the things that are included in there. The main work that was involved in the catalogue was, first of all, compiling timing solutions for all of the pulsars. That allowed us to then fold all the gamma ray data to create gamma ray pulse profiles, which are a key constraint for understanding pulsar emission geometries and so on. And in addition to that, we also have phase average gamma ray spectra for many of those pulsars, which is also related to the emission mechanisms. So these are all kind of the derived sciencey things that we can derive from the inputs to the catalogue. And in the talk, I'll go through some highlights, but if there's anything you're interested in that I don't mention that it is included on this slide, then please ask me. But yeah, as I said, we have 294 gamma ray pulsars with detected gamma ray pulsations. And for 237 of those are bright enough to either have significant pulse profile fitting or gamma ray spectra that are measured from the phase average data. So yeah, the first thing I mentioned is the pulse profile, the collection of pulse profiles that we see from 3PC. And for each of the pulsars in the catalogue, we make a plot like this, where we phase fold the data and create a pulse profile, and then split it into different energy bands, going from a few tens of MeVs up to a few GeVs and above. And one of the things that we found when we did that is that many gamma ray pulsars have this classic double peak shape. And when you split it into these energy bands, we actually find that there's significant evolution of the pulse profiles with energy. So you can see here that the leading peak at low energies is brighter, and as you move up to higher energies, the trailing peak becomes brighter. And that's actually something we see consistently across most of the pulsars in the catalogue. So this plot here is showing the spectral index of the later peak minus the spectral index of the leading peak. And most of them are below zero, which means that the trailing peak has a harder spectrum, and it gets brighter with energy compared to the leading peak. We also have phase-aligned radial pulse profiles for many, not all, but as many as we could of these pulsars. And that also reveals there are significant correlations between the shape of the gamma ray pulse and the lag between the radial pulse and the gamma ray pulse, which sort of matches up with naive expectations that you would get from early emission models. But our goal for this catalogue is to kind of collect observational facts rather than to actually say things about how the emission is created. For the next couple of slides, I'm going to talk about spectra, and I wanted to give a little bit of background to what the gamma ray spectrum looks like from a pulsar. So the gamma ray emission from pulsars is created from the fact that you have relativistic particles that are traveling around curved magnetic field lines, emitting gamma ray photons as they do. And the spectrum that you get from a single particle looks like this. So you have a power law at low energies with a spectral index of, or a photon index of -2/3, and then an exponential cutoff above a certain energy, which we call the cutoff energy, that depends on how curved the path that the particle is traveling along. So that's from a single particle, but obviously we see the sum of lots of particles emission. And they could all be traveling on different field lines and have different initial energies. So what we see is kind of the sum of lots of these lines, and it looks slightly different from this single particle spectrum, where you still have a power law at low energies, but with a different spectral index, and then the cutoff can be a bit slower than a proper exponential. And when you actually look at some real pulsars, then they all have kind of different spectra. So these are 3 different pulsars with spectra ranging from a kind of low energy broad peak up to a slightly higher energy peak, but a much sharper peak with with a harder spectral index at low energies. But it turns out that this way of thinking about the spectrum is not great in terms of modeling, because those low energy and high energy features are very hard to measure. At low energies, the gamma ray point spread function is not great. The sources blend together and you can't tell them apart. Whereas at high energies, the spectrum drops off so quickly that you just don't have many photons to constrain things. And that means that your low energy spectral index and your cutoff energy or your cutoff index are all nastily correlated with one another. So in this catalog, we've moved into a different parameterization where instead we're looking at the curvature of the spectrum around the peak, which is something we can measure well, because this is right in the part of the band where Fermi is most sensitive. Instead of having the low energy spectral index, we're looking at the photon index around the peak where we can measure better. So we're kind of moving away from parameters that are easy to interpret on a physical sense, but to parameters that we can measure better. And when we do that, some trends emerge, some significant trends. So this plot on the left is showing the spectral curvature as a function of the pulsar spin down energy. And this one is the peak energy, the energy at which the spectrum peaks as a function of spin down. And you can see that as you move to more energetic pulsars, then both of these things decrease. So the peak of the spectrum moves to lower energies and the spectrum gets broader. And with the result being that for the least energetic pulsars, which happen to be MSPs in our sample, have a very broad, very narrow and higher energy peak than the higher E dot young pulsars. And that's what this plot on the right is showing. So each of these lines is one pulsar spectrum normalized by E dot. So you're going from high energetic pulsars to low E dot pulsars down here. And showing that these, as you go down this way, the spectra get narrower and get shift to slightly higher energies, with the result that almost all of the emission is situated within a couple of decades of gamma ray energies. The other thing that we learned from the catalog is looking at the pulsar luminosities as a function of the spin down power, which reveals this really strong correlation where the gamma ray luminosity is proportional to the square root of the spin down energy, with a fairly large scatter, but a very significant correlation. And that's also something that was predicted by very basic gamma ray emission models. And the main result is that for this plot on the right is showing the efficiency, so the luminosity divided by E dot. where for the least energetic pulsars in our sample, that efficiency, thank you, is almost 100%. So most of the spin down power that's lost by the pulsar is being emitted in the form of gamma rays. The other thing that we found in the catalogue is that there's no correlation between the radial flux and the gamma ray flux from the pulsar. So this is just a big scatter. And that's actually a good thing for us because it means that as Fermi detects faint sources, there can still be bright radial pulsars in there that we can find with radio telescopes. Which brings me on to the last part of the talk, where we're doing exactly that, using Meerkat, so pointing Meerkat at new unidentified Fermi sources to try and find new MSPs. And this has been a very successful method in the past. About a quarter of known MSPs in the galaxy were found this way. And in particular, this has been great at finding very compact eclipsing binary systems, so redbacks and black widows, where more than 2/3 of those were found by pointing a radio telescope at a gamma ray source. And we're continuing that trend with TRAPUM. So we've now found 21 new MSPs by pointing Meerkat at a Fermi source, of which 10 of them are black widows and redbacks that cluster around this low orbital period part of the MSP population. And with Meerkat, as Michael mentioned, we have high angular resolution, so we can immediately localize a new pulsar that we find to within about an arc second, which is enough to then do immediate optical and X-ray follow-ups, which is great when you're finding black widows that have optical and X-ray counterparts. You can immediately find them. So these are some new redback light curves for some new TRAPUM MSPs. And I believe Oliver is going to be talking to you about modeling some of these new systems in a later talk. And then just the final slide I was going to show is just to come back full circle, where we find a new radio MSP within a gamma ray source, and we can go back and use the Fermi data to back extrapolate its timing solution to in 15 years in the past. And for these are 3 redbacks that we found where if you do that, you find that the orbital period is varying significantly over time due to activity in the companion star. So these color plots are showing the significance of the pulsations as a function of orbital phase on the x-axis, showing kind of complicated and difficult to describe wobbles, basically. But Fermi gives us a great view into these systems that you can't do with timing, radio timing, because it hasn't, when you only find them, you don't have those 15 years in the past. So with that, I'm just going to leave the summary slide up. The main conclusion is that we hope that 3PC will be a big resource for people trying to understand gamma ray and just pulsar emission in general. And that we're also finding lots of fun stuff with TRAPUM. So thank you for listening.
So unfortunately, there's not much time. I mean, it's like many talks in this meeting. Wish it was a bit longer, could show much more of these all these amazing results. We have time for one question. First.
On that plot where you showed the dependence of the gamma ray luminosity on the EDO, so just could you please briefly what are those pale blue dots?
So those are pulsars. They're mostly radio quiet pulsars where we don't have a good estimate of the distance because we don't have a dispersion measure. So for those ones, I think these are upper limits.
Okay, so just if I reformulate your statement that for the pulsar for which you have a good handle on the distance,
yes,
it seems that the gamma ray luminosity depends on the spin down power as a square root of the spin down power.
Yes.
Okay, good. Yeah, thanks.
All right. Thank you. Okay. One more question. Yes.
A very short one. Congratulations for submission. Very wonderful job. Yeah. I think in the second pulsar catalog, you had few pulsars for which even the sub-exponentially cut off spectrum was not really fitting well. I think with Veda, and some else. Do you have more in this new catalog?
That's a good question. I'm not sure exactly. I know for those ones, there's also a very high energy tail. I mean, they're seen with DEV telescopes now as well. So I guess in our catalog, that would probably just be fit with the B parameter being very low. So a very sub-exponential cutoff. That hasn't been what I was focusing on, so I couldn't tell you the answer, but I can have a look.